Bridge, Tensors, Loss, and Backprop. The first technical lecture uses shapes and symbols as a compact language. A formula may describe a batch, a matrix multiplication, a gradient, and a hardware cost in one line. If that notation feels unfamiliar, the lecture can sound harder than the underlying idea. This bridge builds a working vocabulary for tensors, named dimensions, probabilities, loss, and backpropagation. The objective is not to turn this into a mathematics survey. It is to make the symbols readable enough that you can follow the engineering argument. Start with dimensionality. A scalar is one number. A vector is an ordered list of numbers. A matrix is a rectangular table. A tensor is the general name for an array with any number of axes. In machine learning, almost everything is stored as a tensor. Token identifiers, embeddings, model weights, activations, gradients, and optimizer state. A tensor has a shape, which records the length of each axis, and a data type, which records how each element is represented in memory. For language models, three axis names appear constantly: B, T, and D. B is batch size, the number of examples processed together. T is sequence length, the number of token positions in each example. D is hidden dimension, the number of learned features representing each token. A tensor with shape B by T by D can be imagined as B tables, each with T rows and D columns. The names matter more than the letters. Whenever you see a shape, ask what each axis means rather than memorizing a sequence of numbers. Take a tiny example with B equal to 2, T equal to 4, and D equal to 3. There are two sequences, 4 token positions per sequence, and 3 features per position. The tensor contains 2 times 4 times 3, or 24 values. Selecting one sequence removes the batch axis and leaves shape 4 by 3. Selecting one token position from that sequence leaves a vector of length 3. Averaging across token positions removes T and leaves one 3-value summary per sequence. Following what disappears and what survives is the core habit of tensor reasoning.
Shape tells us how many values exist. Multiply the axis lengths to get the element count. Data type tells us how many bytes each value occupies. A tensor shaped 4 by 8 contains 32 elements. In float 32, each element uses 4 bytes, so the tensor uses 128 bytes. In B float 16, each element uses 2 bytes, so it uses 64 bytes. The same arithmetic scales to billions of parameters. Memory accounting is therefore element count times bytes per element, repeated for parameters, gradients, optimizer states, and saved activations. Tensor operations often change the arrangement without changing the underlying information. A transpose swaps axes. A reshape groups or splits axes while preserving the number of elements. A reduction removes an axis by combining values, for example with a sum, mean, or maximum. Broadcasting allows a smaller tensor to participate in a larger operation by conceptually repeating it along compatible axes. These operations are simple individually, but code becomes confusing when axes are referred to only by positions, such as -1 or -2. Named dimension tools, such as inops, make the intended transformation explicit. Instead of saying transpose axis 1 and axis 2, we can say that a tensor changes from batch sequence hidden to batch hidden sequence. Instead of remembering which dimension to sum, we name the dimension that disappears. The exact library syntax is less important than the discipline it encourages. Track dimensions by meaning. If an axis appears in the inputs but not the output, it is usually being reduced. If it appears in the output, it survives. For example, attention begins with query and key tensors that may have axes batch, head, token, and head dimension. The score operation pairs every query token with every key token and sums over head dimension. The output keeps batch and head, keeps one axis for query position, keeps one for key position, and removes head dimension. Written with names, the intended result is almost a sentence. Written only with transposes and negative axis numbers, the same operation can be difficult to audit. Named axes turn shape checking into a lightweight proof.
Matrix multiplication follows that same rule. Suppose an input matrix X has shape B by D, and a weight matrix W has shape D by K. The shared D dimension is consumed by multiplication and summation. The result has shape b by k. For each of the b examples and each of the k output features, the operation forms a dot product across d input features. That costs roughly 2 times b times d times k floating point operations, 1 multiplication and approximately 1 addition for each contribution. Use small numbers to make the rule concrete. Let x have shape 2 by 3 and w have shape 3 by 4. The result must have shape 2 by 4. It contains 8 outputs. Each output combines 3 pairs of values, requiring 3 multiplications and roughly 3 additions. That is about 6 operations per output, or 48 flops in total. The formula 2 times b times d times k gives 2 times 2 times 3 times 4, also 48. Large model accounting is this same arithmetic with much larger dimensions. The transpose symbols that appear during backpropagation are not arbitrary decoration. Matrix multiplication requires the shared dimensions to line up. In the forward pass, x times w maps d input features to k output features. When we later ask how the loss changes with respect to x or w, we must align the same axes in a different order. Transposes place the shared dimensions where the multiplication can consume them. A reliable way to check a gradient equation is to ignore the calculus for a moment and verify that its output shape matches the thing whose gradient we want. Now connect tensors to language prediction. At a token position, the model produces 1 score for every vocabulary item. If the vocabulary contains 50,000 tokens, the score vector has 50,000 values. These scores are logits. A logit is not a probability. It can be positive or negative, and the values do not add to 1. What matters is their relative size. A token with a larger logit is preferred over a token with a smaller one.
Softmax converts logits into probabilities. It exponentiates each score and divides by the sum of all exponentiated scores. Exponentiation makes score differences matter strongly, while division normalizes the results so they add to 1. If one token has a much larger logit than the rest, its probability approaches 1. If several logits are similar, probability is distributed among them. In practice, implementations subtract the largest logit before exponentiating. That changes none of the probabilities, but prevents numerical overflow. Consider 3 logits, 2, 1, and 0. Their exponentials are approximately 7.4, 2.7, and 1. Dividing by the total gives probabilities near 0.67, 0.24, and 0.09. Adding the same constant to every logit leaves those probabilities unchanged because every exponential receives the same multiplier. This is why subtracting the maximum is safe. Multiplying all logits by a large factor, however, makes the distribution sharper. Temperature sampling uses that fact by scaling logits before softmax to control how concentrated or varied generation becomes. During next token training, the dataset supplies the correct token. Cross-entropy loss looks at the probability assigned to that correct answer and takes its negative logarithm. If the model assigns probability 1, the loss approaches 0. If it assigns probability 1/2, the loss is about 0.69. If it assigns probability 1,000th, the loss is about 6.9. The logarithm turns multiplication across many predictions into addition and heavily penalizes confident mistakes. The loss for a batch is usually averaged across token positions that count toward training.
Sequences in one batch may have different useful lengths, so training often includes a mask. The mask marks which token positions contribute to the loss and which are padding or otherwise excluded. Cross-entropy is computed at each active position, summed and divided by the number of active targets. This detail matters when comparing runs. Averaging by sequences instead of valid tokens can weight short and long examples differently. Even a single scalar loss therefore has a shape story underneath it. Perplexity is the exponential of average cross-entropy. It can be interpreted loosely as the effective number of choices the model is uncertain among. A perplexity of 10 suggests uncertainty comparable to choosing among about 10 equally likely options, although real distributions are not uniform. Perplexity is useful for comparing language models on the same tokenization and dataset. It is not directly comparable across different tokenizers because changing token boundaries changes what counts as one prediction. The forward path can be viewed as a computation graph. Tokens select embeddings. Layers perform matrix multiplications, attention, nonlinear transformations, residual additions, and normalization. The final representation produces logits.
softmax and cross-entropy produces scalar loss. Each box in that graph remembers enough information to determine how a small change in its input would affect its output. Backpropagation walks the graph in reverse and combines those local effects. A tiny graph shows the idea. Let an input x be multiplied by weight w to produce h, then let the loss be the square of h minus a target. The loss depends on h, and h depends on w. To learn how the loss changes with w, first ask how the loss changes with h, then how h changes with w, and multiply those answers. A framework records these relationships during forward and evaluates them backward. Deep networks contain far more nodes, but automatic differentiation repeats the same local rule.
The chain rule is the organizing principle. If A affects B and B affects the loss, then A affects the loss through B. Multiply the local sensitivity of B to A by the sensitivity of the loss to B. In a deep network, backpropagation repeats this logic from the loss back through every layer. Automatic differentiation performs the bookkeeping, but the meaning remains concrete. Assign responsibility for the final error to every intermediate value and every parameter. Consider a linear layer, h2 equals h1 times w. Suppose the gradient arriving from later computation has the same shape as h2. To compute the gradient with respect to h1, multiply the arriving gradient by an appropriately transposed w. To compute the gradient with respect to w, combine h1 with the arriving gradient and sum over the batch or token positions that use the same weights. The first result must have h1's shape, the second must have w's shape. This is why the backward pass of a linear layer needs roughly 2 matrix multiplications, while the forward pass needed 1. Suppose h1 has shape 64 by 4096, and w has shape 4096 by 11008. h2 then has shape 64 by 11008. The incoming gradient also has shape 64 by 11008. Multiplying it by w transposed produces 64 by 4096, exactly h1 shape. Combining h1 transposed with the incoming gradient produces 4096 by 11008, exactly w shape. You do not need to memorize the formulas. Demand the correct destination shape, identify the shared axis, and the transpose becomes much easier to reconstruct. That observation explains the 6ND training estimate. For each token, a dense model uses each parameter in roughly 1 multiply add during the forward pass, about 2 operations. Backward computes gradients for activations and parameters, costing about twice the forward pass, or 4 more operations. 2 plus 4 gives approximately 6 operations per parameter per token. Multiply by n parameters and d training tokens to get about 6 ND flops. Attention and other operations add corrections, especially at long sequence lengths, but the estimate is remarkably useful.
Gradients are not parameter updates by themselves. Stochastic gradient descent subtracts the gradient multiplied by a learning rate. Atom-style optimizers also maintain moving averages of gradients and squared gradients, then use those statistics to scale updates. This improves behavior, but adds memory. Parameters might use 2 bytes each in bfloat16, gradients another 2, and 2 atom moment tensors 4 bytes each in float32. Before counting activations, that is already roughly 12 bytes per parameter. For a 7 billion parameter model, 12 bytes per parameter is about 84 gigabytes. That already exceeds the memory of many single GPUs, and it still excludes activations, temporary buffers, and framework overhead. This is why optimizer sharding and distributed training appear so early in systems discussions. The model may fit for inference at 2 bytes per parameter, but fail to fit for training because training carries several additional copies and states. Model size is incomplete unless we ask which phase and which tensors are included. Precision determines both storage and numerical behavior. Float32 uses 4 bytes and offers substantial range and precision. Float16 uses 2 bytes but has limited exponent range, which can cause overflow or underflow. bfloat16 also uses 2 bytes, but preserves the exponent range of float32 while keeping fewer precision bits. That trade-off works well for many neural network operations. Mixed precision training commonly uses bfloat16 for parameters, activations, gradients, and matrix multiplication, while retaining float32 for sensitive accumulations and optimizer state. Activations create another memory category. Backward needs intermediate values from the forward pass, so training saves activations for many layers.
Their size grows with batch, sequence length, hidden width, and depth. Gradient accumulation processes several smaller microbatches before one optimizer update, reducing peak activation memory while preserving a larger effective batch. Activation checkpointing saves fewer intermediate values and recomputes them during backward, exchanging additional flops for lower memory use.
You now have a practical method for reading the lecture. For any tensor, name the axes, multiply them to count elements, and attach bytes from the data type. For any matrix multiplication, identify the shared dimension that disappears and the dimensions that survive. For any gradient, verify that its shape matches the value it describes. For any probability or loss, ask what event is being scored. For any hardware estimate, separate total work, measured in flops, from execution rate, measured in flops per second. With those checks, the notation becomes an accounting system rather than a wall of symbols.